Okay, so this is our next example with the first derivative analysis. This is a this is a rational function, x over x squared minus 4. So we're going to do the same process, the first derivative analysis. So the derivative, this requires the quotient rule. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And if we simplify the numerator, this becomes x to the second minus 4 times 1, x to the second minus 4, and then it's also minus 2x to the second. So this numerator simplifies to negative x to the second minus 4. The denominator is x squared minus 4 to the second power. We're going to find the critical values. Type 1. That's where the derivative is equal to 0. And so we have our rule that if a fraction is equal to 0, then you may set the numerator equal to 0. So the derivative is equal to 0 occurs only when the numerator negative x to the second minus 4 is equal to 0. And what do we have there? We're going to solve that. I have negative x to the second is equal to 4, or x to the second is equal to negative 4, and we can see that has no solution. If you try to take the square root of both sides of the equation, we would get a non-real, an imaginary value. Since we're doing the real value calculus for our purposes, we would say there's no solution. So there are no type 1 critical values. Remember, no solution does not mean wasted time. No solution means whatever you're looking for, in this case type 1 critical values, whatever you're looking for, there aren't any. Type 2 critical values, that's where the denominator is equal to 0. So that's where the function is not defined, or excuse me, the derivative is not defined. Well, that would be where the denominator is equal to 0. So where is this not defined? We want the type 2 critical values. That's where the derivative fails to exist. So the derivative is here. Where does that function fail to exist? It fails to exist if the denominator is equal to 0. So this would occur when x to the second minus 4 to the second power is equal to 0. A function fails to exist if a function fails to exist if the denominator is equal to 0. Well, the denominator equal to 0 is here, and so that gives us, take the square root of both sides of the equation, x to the second minus 4 is equal to 0. That gives us that x is equal to 2, or x is equal to negative 2. So we have two type 2 critical values, 2 and negative 2. All right, so here is our number line. Our two cut values, the only two cut values we have are at 2 and at negative 2. And we need to find where this function is increasing and where it's decreasing. So we're going to choose representative values from each region of the number line. So there's negative 1, I'm going to use 0, I'm going to use positive 1, and we'll see what the function is doing in each of those regions. So the derivative at negative 1, we need the derivative at 0, and we need the derivative at positive 1. Well, the derivative is the negative x to the second minus 4 over this x squared minus 4 quantity squared. At negative 1, what do we have? We have negative 1 squared minus 4 over negative 1 squared minus 4 quantity squared. Now we can see that no matter what value we choose, this denominator is going to end up being a positive value. All we're concerned with is whether this value is positive or negative. And so we have negative 1 squared is 1, the negative of that minus 4. And so what do we have here? That gives us negative 1 minus 4 over, this is a positive value. Can we see this? Negative 1 to the second minus 4 quantity squared. So no matter what value this is, it's going to be a positive number. And so negative 1 minus 4, this is a negative value divided by a positive value. All right? And so we know this is negative, which means the function is decreasing in that interval. So in the interval from negative infinity to negative 2, the first derivative is less than 0, the first derivative is negative, the curve is decreasing in that interval. All right? So let's check the value at 0. At 0, what is the function doing? We need to insert 0 into, or evaluate the first derivative at 0. So this is negative 0 squared minus 4 all over. Now we've already determined that irrespective of the choice for x, this denominator is always going to be a positive number, because the last thing you do in the denominator is you square that value. So the denominator at 0, 0 squared minus 4 is negative, but squared is always a positive number. So all we're left with is what is happening in the numerator. Well, that's negative 4, which is a negative value over a positive value. Negative divided by positive is negative, which means the curve is decreasing in that interval as well. And then the last piece is what happens in this interval from 2 to infinity. And so that is found by using the derivative evaluated at 1, and negative 1 squared minus 4 over, and again, we've determined this several times now, the denominator is always going to be positive irrespective of the choice. Negative 1 minus 4 is a negative number. So again, we have a negative numerator and a positive denominator. That means the derivative is negative, which means the function is decreasing. All right? So the function is decreasing from negative infinity to negative 2. It's decreasing from negative 2 to 2, and it's decreasing from 2 to infinity. So we can write that. F is decreasing, and write out those intervals. Negative infinity to negative 2, negative 2 to 2, and 2 to infinity. Now, we can see that there are no relative extrema. In order to have a relative extremum, you need to either be going downhill and changing to uphill, meaning you've bottomed out in the valley, or you need to be going uphill, changing to downhill, meaning you've topped out over the hilltop. In this case, you're going downhill, continuing to go decreasing, continuing to be decreasing, and so this curve never has any relative extrema. One last piece is this. You should not attempt to combine these intervals into one grand answer, and the reason is because, particularly in this case, but in general, you don't know necessarily that they do actually combine. In this particular case, we can see from this, from our knowledge of basic algebra, basic college algebra, we know that this function has asymptotes at 2 and negative 2. The graph of this function is something like this. It's decreasing in this interval, we saw that. It's decreasing in between, we saw that. And it's decreasing in this interval. And so this curve is decreasing in all three subintervals of the real number line, but it is not decreasing if you try to combine them. If you combine these intervals, then you would say that this point is decreasing and continues to decrease as you go into the other interval. That's not what happens. The moral of the story is, when you write these intervals, increasing, decreasing, it is best practice to simply not combine. There are some circumstances where you may combine them, but it is never incorrect, it is never wrong to simply leave them as separate intervals. And so that's what you would do for this work. And so in this case, this function is decreasing on all three intervals, and there are no relative extrema.